We're going to try and finish up chapter 8 today. I think I have all the homework open for the rest of the semester, and I think we're in good shape on other stuff. So we're going to progress today a little bit, and I'm hoping to finish class a little early today so that we can get things. Yeah. All right. Was there a question over there in Takawa? Yes, the Wednesday after Thanksgiving break. Yeah. I'm trying to be nice. I'm trying to get a break just like everybody else. It's okay. All right. So we've been doing torque. And I did get the lecture posted for everything. And remember that torque is going to be our distance across, cross product with the force, and that ends up being RF sine theta. And if I'm looking at, we'll make this is the z-axis, this is the y-axis, and this is the x-axis. If I have an R vector, and then I have a force that's applied to that vector, the angle is going to be right here. That's where my angle is going to be. We've talked about conditions of equilibrium. And those conditions of equilibrium were that the sum of the forces has to equal 0 and the sum of the torques has to equal 0. We finished on Wednesday with looking at center of gravity or center of mass. And that looked at my x of the center was going to be the sum of the individual masses times the radius or wherever they were located divided by the sum of the masses. And I can do that for y as well. And I can do that for z as well. And that's kind of where we were. And then I also hinted at that this related to my acceleration being 0, and I related that this was related to my angular acceleration being 0. And I think that's where we left it. Okay? So I'm going to define something today that if we're dealing with forces, so if I'm looking at forces, we worry about mass, and we talk about inertia, and when we were dealing with that, we knew that if I had a mass m or I had a little mass m, that more force was going to be required to push that mass than that mass. So we knew that inertia was like the resistance to motion. Now, when I have things that are rotating, and we hinted at this at the end of Wednesday, so if like a bicycle wheel that was rotating, that it's harder to stop when it's rotating. And when I'm dealing with rotational motion, I still have inertia, but now we worry about something called the moment of inertia. Okay, we can worry about something called the moment of inertia. And the moment of inertia we're going to use as a letter I, and we're going to define that as the mass radius squared. So if I have a disk or a circle, I'm out here at a distance r. There are usually, for disks and spheres and things like that, we have generalized formulas for moments of inertia, but I can also do like a baton. And let's say we're going to rotate around this axis. I can calculate a moment of inertia for this because I'm looking at where those individual masses are, just like I was looking for where those individual masses were when I was dealing with the center of mass. So we get something called a moment of inertia. And we'll actually work a problem today that kind of looks at a lot of those things. So I've got moment of inertia. So my moment of inertia is going to be defined like this. We've got the sum of the forces, because I want to show you the parallels here. We got some of the forces look like that. And then I hinted at the end of Wednesday that we could look at torque being the moment of inertia times the angular acceleration. So I have some parallels that I can play with. But let's also look at what's happening when I'm rotating something. So I've got rotation there, and we talked about if I'm looking at something called a flywheel, that I can store energy in a flywheel, because that's a storage device. And if you've ever looked at an old square baler, you'll see that lovely storage device in terms of that big flywheel that they have on there that help carry things through. And in my linear motion, we know that kinetic energy is 1/2 mv squared. And we know, because we've been talking about it, that V is equal to R omega. So I can go in here and look at it in terms of rotation. So now I've got R omega squared, which now becomes 1/2 mr squared omega squared, but we just defined that as something else. And now this is 1/2 I omega squared. And this is kinetic energy of rotation. So that becomes my kinetic energy of rotation. So we're going to look at a problem here. Okay, we're going to look at a problem. We're going to start it because it's always fun to kind of look at some things. Okay, it's always fun to look at it. We've got our person. So here's our person, and he's got a slingshot with a rock. Our good old David and Goliath problem. And we're going to start rotating this pebble or rock around in a circle at 10 revolutions per second. And we're going to be conservative and say that this is a 1/2 meter in radius. And we're going to use the mass of my rock to be 0.25 kilograms. What we're going to want to calculate, first we want to calculate the angular velocity. We want to calculate the moment of inertia. And we want to calculate the kinetic energy. So let's do the angular speed first, right? So this is, we've got it in revolutions per second, but we want it in radians per second. And so we know we've got to take our 10 revolutions per second and convert that to radians, and there are 2 pi radians per revolution. So now I'm going to have 20 pi radians per second being my angular velocity. My moment of inertia is just going to be my mass times the radius squared, and that's going to be my 0.25 kilograms times my radius, which was 0.5 meters. We've got to square that, and this is kilograms. So we end up in weird units of kilograms meters squared. So I got 0.25 times 0.5 squared gives me 0.06 0.25 kilograms meters squared. And now we can calculate the kinetic energy. The kinetic energy is 1/2 I omega squared. So that's going to be 1/2 0.0625. And I've got 20 pi squared. Which, if I do this, this makes it 10 pi. I think that's right. Should be all right. Not sure I want to do that just yet. Let's do the square. Let's leave it in there. Plug it in the calculator correctly. 20 times pi. We want to square that. We want to do it times 0.0625. Divide by 2 gives me 123 joules. And this is in kilograms meters squared. And this gives me my seconds squared. So kilograms meters per second squared is a Newton. And my extra meters gives me a Newton meter, and I'm in joules. So we get our joules. So we've got David and Goliath playing out there, but we're going to take this problem a little bit more. So we're going to look at our problems. We've actually calculated the kinetic energy, and we've got the rock. So now when the rock is released, we know it's going to go out somewhere, and we have conservation of energy. And so the kinetic energy that was developed in rotation now ends up being the kinetic energy that's in translation. And this is just based on conservation of energy. So what we want to know, since this is the David and Goliath problem, we want to know how hard the rock hits Goliath. Okay? We want to know how hard the rock hits Goliath. So if we're going to say David is about 6 feet tall, so we're going to be up at 2 meters, just to make it easy to deal with. And we're going to actually say that the sling was 0.3 meters above his head. I can't spell today. So we want to calculate is what is the total energy of the mass as it leaves the sling. So now the total energy is going to equal what my kinetic energy is plus my potential energy. So my kinetic energy we've already calculated, which was 123 joules. And that's going to be mgh that we have to figure in. And so that's 123 joules plus my 0.25 kilograms, 9.8 meters per second squared. And we're at 2.3 meters when we start off. And that gives us 5.6 joules. And we're going to add that to the 123 joules. And that's going to give us 128.6 joules. So we have how it would go. We could look to see the range of the rock. So let's look at the range of the rock. You can see how far the rock travels. So in that case, what we've got, drawing our picture, so we've got our rock up here, and we know once it leaves, it's going to do a projectile motion, because we've done that before. The change in y is going to be 2.3 meters. And so I can do that my change in y is going to equal my initial velocity in the y direction minus 1/2 gravity times time squared. And we know that the initial velocity in the y direction is equal to 0, because once it leaves here, it's going to go only out in a velocity in the x direction. So I can do the same problem that we've been doing all along. Minus 2.3 meters is equal to minus 1/2 gravity times time squared. If I solve for time, that's going to equal the square root of 2 times 2.3 divided by 9.8. And that gives me 0.685 seconds. So my change in distance is going to equal the velocity in the x direction times time, but my velocity in the x direction is going to be r omega. And so my velocity in the x direction is going to be 0.5 meters times my 62.8 radians per second, which is our 20 pi. And that gives me 31.4 meters per second. And now my change in distance is going to be 31.4 meters per second, 0.685. It's going to equal 21.5 meters. So he could hit somebody, or at least he'll hit the ground 21.5 meters away. Now, if he's closer to Goliath, and then we actually say, all right, let's look at what happens here. We actually have a velocity of our rock. We just calculated the velocity of our rock. So there's our translational velocity of the rock. So we can calculate the momentum of our rock. So the momentum of our rock is going to be 0.25 times my 31.4 meters per second. That's going to give us momentum. 0.25 times 31.4 gives us 7.85. This is kilograms meters per second. So if we want to know the force that's applied, because remember, it's not the fall that kills you, it's the really quick landing. So if we want to know the force applies, and let's say it applies over 1/10 of a second, we're going to take our change in momentum, which is 7.85, divided by our 1/10 of a second, and that's going to give us something like 78 newtons. So we can actually utilize lots of things that we've been doing in order to calculate a variety of different aspects. All right, there's one more thing that we've got to do. And we've all seen it, and I will post them hopefully today, but maybe not, maybe sometime over break. But we've all seen this. Winter Olympics time, we've got our figure skater, right? We've got our figure skater, and our figure skater is in a really tight spin, okay, going around in a circle at a really tight spin, and we know that the angular velocity is pretty fast. We also see that same figure skater, I love my artwork, right? We all love my artwork, that's standing out like this, and it's going around, and the omega, the rotational speed is fairly slow. The question is why? Okay? The question is why? One of the things that we know, and I can actually kind of draw it here, is the effective radius of this skater, we call that R1, and the effective radius of this skater, we call this R2. R2 is bigger than R1. And we just saw that I have a moment of inertia that's related to that R. That my moment of inertia is related to that R. And it's going to be highly dependent because if I'm spinning, so let's look at something to spin something here. So let's look at a baton like this. And if I'm spinning this baton, and each one of these is an R, the moment of inertia for that baton is going to be the sum of those individual little batons. So if these are M and M and M and M, and I'm rotating it, so this is actually rotating so that the X is rotating. So it becomes very important as to what axis I'm rotating it on. So in this case, this is going to be 4 mr squareds because I have one mass at each of the corners and they're all r apart. Now if I take that same baton and I look at it from this way, and now I'm going to rotate it around this axis, so I've only got the 2 masses there, and these 2 masses are along the axis of rotation. So this is for this situation where I have 4 about the center. This one, if I look at the sum of the MRs, I've got the first one is at 0, the second one is at 0, and then I have 2 at mr squared, and I've got a different moment of inertia for the different situation. And we know that because we can spin, and we've played with those spins, and we've also done this kind of a spin because we've all done it on our office chairs, right? We get it going spinning around, and if I pull my arms out and I pull my arms in, I'm changing the effective radius, and so I'm getting something that's happening a little different. And we've talked about momentum. So linear momentum looks like mv, right? Now I'm going to talk about something called angular momentum. And we can look at this for a second. If I look at angular momentum, I can write this. This is, we know that V is equal to R omega. No, that's not right. Yeah, that's right. V is equal to R omega. And I can actually look at this as MVR if I want to do a rotational portion, or I can look at it as, we define it as L I omega. And if I do that, let's kind of look at it real quick. If I do I as M R squared omega, when we get the MR R omega, then we get the MRV. It's an R and that's a V. That's how you can go from here to there. So we have a couple of ways of writing it out. One of the ways, but we actually define this, and so we use L I omega squared as angular momentum. God, can't spell. So we can look at our figure skater. So we've gone from there to there to there. So let's look at our figure skater. So if I have a figure skater that has a mass of 50 kilograms, and we're going to do the skating where the arms are out, and so the effective radius here is 0.5 meters, and then we're going to look at when they're all scrunched up, and the effective radius is 0.25 meters. We have conservation of angular momentum, just like we have conservation of linear momentum. So mass 1, velocity 1, radius 1 has got to equal mass 2, velocity 2, radius 2. Masses are the same. We didn't change masses. So now, if I go from one to the other, velocity 1, radius 1 is equal to velocity 2, radius 2. We're going to go from this one to that one, so we want to solve for velocity 2. So I'm going to have R2 on both sides. So my velocity 1, and if this is 0.5 divided by 0.25, the speed essentially doubles when I shrink down the radius. So my skater is definitely going to go faster. Or if I go longer, it's going to it's going to slow down. So we can work it back and forth. So we get angular momentum. We can also relate angular momentum to torque. So here's my torque. My torque is my moment of inertia times my angular velocity. But torque is going to do something very similar that we've seen before. I can have it as a change in angular momentum with respect to time, just like I did with forces. Forces is mass times acceleration, but force was also a change in momentum with respect to time. So I can do that. And we know what L is, right? L is now I omega, so I can do a change in that with respect to time. And so we don't usually change our moment of inertia, just like we don't usually change the other. So I can look at it as well. So we've got similar types of problems that we can play with, just like we have done in the past. So now what I'm going to do is I'm going to give you the cheat sheet for where we have come from, which kind of summarizes everything that we've done so far. Okay, so if I were developing a cheat sheet for physics class, at this point, because we're getting close to the final, right? And yes, you can have a cheat sheet on the final. And the final in this class is comprehensive. About the only additional thing that will go on this cheat sheet, and I'll actually write them on here at the bottom so that you actually have it, we'll get you as follows. So we have done, so far, we have done coordinate systems. And this is why I like writing it over here like this. We've done coordinate systems where this is R, this is Y, this is X, and there's my angle. And I have the sine of the angle in this context is Y over R. Cosine of the angle is X over R. Sine of the angle is equal to Y over X. We also can convert to our rotational point of view, where this is R, this is my angle, and this point is in R theta. So we've looked at two different coordinate systems. Also, R is going to equal the square root of X squared plus Y squared. We've done kinematics, where we've had velocity is equal to the initial velocity plus the acceleration times time, as long as I have a constant acceleration. We've done the change in position is equal to the velocity times time plus 1/2 AT squared. And we've done V squared is equal to V naught squared plus 2A times my change in position. It's an X. I can do the same thing for rotation. Change in angle is equal to omega times time plus 1/2 alpha t squared. And I've got omega squared is equal to omega squared plus 2 alpha times my change in angle. And we also have that that this omega is equal to a change in angle with respect to time, and that we have velocity tangential is r omega. acceleration tangential is r alpha, and we have a centripetal acceleration as v squared over r, which is also r omega squared. We've done the sum of the forces is equal to mass times acceleration. We've done Newton's law of gravitation, where G is equal to 6.67 times 10 to the minus 11 Newton meters squared, kilograms squared. We've defined work as a scalar product of the force times the distance, and that equaled force times the distance cosine of the angle. And we've defined torque, which is a vector quantity, as r cross f, which is equal to rf sine of the angle. Oops. Sine of the angle. We've looked at kinetic energy, which is 1/2 mv squared, or it is equal to 1/2 I omega squared. We've done momentum, as in the book does it with a P. We've done that one. And we've done angular momentum as I omega. We've got power is equal to the work divided by the change in time. Or we can look at it as force times velocity, even though we didn't use it that much. We've got potential energy is equal to mgh, and we also have potential energy for a spring is equal to 1/2 kx squared, and we have a force due to a spring is equal to minus kx. We have that force can equal a change in momentum with respect to a change in time. Torque is I omega, or I alpha, and that's a change in angular momentum with respect to time. And we have I, because we might need it, is the sum of the mass times the radius squared. And I think I've got everything written down, except for the two that we will see coming up in chapter 9. And that is pressure, which is what we're about to start looking at. Pressure is equal to force per unit area. And since I can't do that one off the top of my head, Bernoulli's equation, but we'll get there. We'll get Bernoulli's equation as well. And then the other things that we have, even though we don't have an equation, we have conservation of energy. We have conservation of energy, mass, and momentum. And that's both angular and linear momentum. And if I were writing a cheat sheet for physics final, that's what I would write. I have a nice neater one. The nice neater one looks like this, because I can write it in smaller pen. And again, this one is missing, this particular one is missing the items associated with pressure, which is what we're going to get to in the next chapter, and Bernoulli's equation. That's what we'll end up with. So if your guys are starting to study for the final, because unfortunately, as you can see, Physics 1, there's no way I can avoid giving you a comprehensive final. because everything is built upon itself so far. We'll start to see a few odds and ends, different things coming up in the next couple weeks, but pretty much everything to this point has been built up on the same stuff. And we only have 4 lectures between now and the final. We're getting close. We're getting close. Reminder to everybody, if you haven't gotten enrolled, they're opening up classes to OSU starting right after break. So some of the classes will have a tendency to fill. Any questions? I don't know yet. I haven't made it. It's going to be a 2-hour final, so it's probably going to be something on the order of working problems. It'll be something on the order of 20 to 25, but it may be longer because I may have some real quick knockout conceptual problems that'll be on there that don't require a whole lot of calculation or work. So it's probably going to be on the order of 25 to 30 questions for the final. Y'all have a good Thanksgiving. Stay safe and warm.
There's no anatomy.